Hey, this chapter is about abrasive machining and finishing operations. And in all of these processes, our material removal rate is not higher, it's low compared to other manufacturing processes, other machining processes, since our main aim is to increase the surface quality and decrease the surface roughness. In all these processes we are going to cover, as you see, you're responsible from all these sections. And it's such processes, as I said, we will be focusing more on the dimensional accuracy and surface quality of the surfaces. And there are many types of such processes. And in all of these, almost all of them, we are removing material with the mechanism of abrasion due to the contact between some tools and workpiece surfaces. We will be removing material. And let's start from an abrasive. What is an abrasive? Actually, abrasives are very little particles. You see two examples here. The first one is made of aluminum oxide, and the other one is a diamond example. Diamond has, as you see, much better surfaces, a bit regular than the aluminum oxide. But the thing is that they are quite small. And as you see here, their sizes, their cutting edges are usually around 100 micrometers. And another important issue about abrasive particles is that although they are small, they have many cutting edges. They don't just have a single point cutting edge, they have many cutting edges. And another issue about compared to the single point cutting tool is that their material removal, or the amount of material they can remove, is very low. They can produce tiny chips. So that's why actually we love to use them together, many thousands of them at the same time on a paper or a kind of a wheel, so that the material removal rate will be increased a bit better to very acceptable levels, and we can do some finishing operations. And the simplest type of abrasive particles and sands, and there are obviously some edges that it has an irregular shape. So these are the things I can say about abrasive particles. In all of these abrasive machining processes, we make use of somehow these little abrasive particles. And with the help of these actually abrasive particles, which are sometimes embedded onto papers or mounted around the wheel, with the help of them, we increase the quality of the surfaces or remove some materials from sharp corners or sharp edges, so that our dimensional accuracy and surface quality will be improved. You can see some types of abrasives and some wheels, some papers here. They can all be used for abrasive machining, and with the help of them, we can have dimensional tolerances maybe less than 1 micrometer, and surface roughness values even less than 25 nanometers. And these are called, actually, these processes are mostly called as finishing processes, since our aim is to improve dimensional accuracy. We are not removing too much material, we are removing less material, and try to make our surface qualities better. And in this chapter, we'll be talking about all these processes, issues, some other finishing operations. And here in this figure, you see some different types of grinding operations. The first one is cylindrical grinding, and then we may do also grinding operations on conical surfaces. We can produce such fillers, even threads can be manufactured, obtained with the help of grinding processes. And then we can work on the interior surface of some cylindrical shapes. We can open grooves, many grooves at a time, and other internal grinding operations. So these are some types of grinding or abrasive machining operations we are going to discuss in this chapter. But before we start discussing the operations, it's better we spend some time on abrasives and bonded abrasives. And you see we have two types of abrasives, the conventional ones and the super abrasives. In the conventional ones, we have only two types: aluminum oxide, ceramics, and silicon carbide. And depending on actually the type of workpiece you want to actually grind, you should go with one of them. If it's carbon steel, ferrous alloys, or alloy steel, so if it contains some iron inside, then you should go with aluminum oxide. But for non-ferrous metals or other types of materials, silicon carbide is a bit better option. And on the other hand, we have some super abrasives. These are cubic boron nitride and diamond. And obviously, we use them for the workpieces having much higher hardness value, since, as you know, if you want to remove material from a workpiece, you need to have tools having higher hardness values than the workpiece. So for such cases, you may go with CBN or diamond, and you know that for the steels we cannot use diamond. If that's the case, you should be using cubic boron nitride, but there might be some exception. If the actually the hardness of your tool is much important than the reactivity of your diamond with carbon in the steel, then you may still go with diamond. But for most of the time, we don't prefer to use diamond for steels. Instead, we prefer to use cubic boron nitride type of abrasives or bonded abrasives. And we have an important property or characteristics of abrasives. This is called friability, and it's actually the ability of the abrasive grains to fracture into smaller grains. Why it is important? Since once you do the abrasive machining, we will be generating some little chips, and after some time, due to high amount of abrasion, their cutting edges may become dull. So at some point, they need to resharpen themselves. And this property is called as friability. With the help of it, the dull edges, the dull parts actually broken, and we will have new edges, new grains inside, so that we can continue abrasive machining operation. So if I say, for instance, specific grinding wheel has high friability, then that means it has low strength, low fracture resistance of the abrasives are there, so it can easily resharpen itself. You don't need to remove the grinding wheel, sharp it, and then reinstall it again. You don't need to do that. It is actually resharpened itself easily since it has high friability. So I talk about grinding wheels. So what are grinding wheels? These are such kind of circular tools, and we said that, if you remember, the grains here, the abrasive particles are very small. They can remove little chips. So that's why we use many of them actually at the same time. So for that purpose, we may be using some simple belts or papers, but it's better we go with some type of wheels. As you see here, there are probably about millions of such abrasive particles on it, and they are bonded together with the help of such special bonding materials. Depending on the type of abrasive you are using, they may change, but for most of the time they are using resin type of material. Another issue about the wheels is that we need to have some porosity in between these grains. They are highly useful, since while we are doing the abrasive machining, some little chips will be generated, and we will be using these porous regions to store these chips, like in the case of broaching and sewing processes. So these are some kind of gullets, chip gullets, and at let's say after some hours of operation, if these are not broken, if these chips are not removed, then we need to do some dressing operations. I will talk about them in a moment, but these are the things we should know about the grinding wheels, why we use them, since we want to increase the material remove rate of abrasive machining process. And here you see some typical wheels. Depending on your actually workpiece you are working on, you may select the right one, having larger, smaller, or conical surfaces. And some companies have such actually marking systems, but you're not responsible for these parts. I'm not going to discuss all these issues since they change from company to company. Now I will be talking about briefly on the grinding process. And as you have seen, we are not using single point cutting tools as we were using in the other machining processes. We are using little abrasive particles mounted on a wheel or paper or kind of thing. So we have many abrasive particles which are removing material from the surface of our workpieces. So what are the differences with respect to such single point cutting tools? First of all, these abrasive grains have irregular shapes. They have many cutting edges. Another issue is that they have negative rake angles in average. Actually, and this negative rake angle is quite high. As you see, it's around minus 60 degrees. And so that's why actually we have the chips undergoing plastic deformation, which is not actually the case in the other machining processes. Another issue about the grains is that they are not always removing material. They may be passive, and depending on their orientation, their positions on the wheel, they may not be active. But at the point, once the actually grains on the outer surfaces are removed, then you may be using the grains inside. Another thing with respect to the single point cutting tools is that the surface speed or the cutting speeds in grinding wheels are quite higher compared to other machining operations. You can see a typical sketch here. This is our grain, and you can see that we have a higher rake angle, negative rake angle, and we have a little shear angle phi. So this is quite difficult to remove material. We have more plastic deformation compared to the actually other machining processes. And you're not responsible from the little mats behind the material removal rates. And I want to talk about a little on the grinding ratio. And as we discussed, grinding wheels are highly utilized in abrasive machining processes. And we have a specific ratio for these wheels. What is that? It's actually the ratio of the volume of material removed in the process to volume of actually wheel wear. So assume that you are removing, let's say, 20 units of material, but since due to this actual relative motion, also we will have some amount of wear on our grinding wheel. So if you remove 20 units of material and you have 1 unit of wheel wear, then the ratio will be equal to 20. And our aim is to always increase this ratio, since once this ratio is increased, then that means you can use the same grinding field for a longer time, do more machining, and remove more material. And you can easily increase it actually if you use some type of grinding fluids, very similar to cutting fluids we were using in other machining processes. So if you use such fluids, then probably your grinding ratio will be increased by 10 times.